Good.
Okay, so what we've decided to do for fun is to treat the 5x5 problem. Now, knowing that we're not going to do any sort of 5x5 determinant, but if we have a molecule like this, which is 1,4-pentadiene nil radical, you can look that up and find a very fine paper from this university on this radical. It's got, again, I mean, these are all sp2 hybridized carbons. It leaves a p orbital on each carbon that lines up, and they form delocalized NOs. Now, I've symmetry adapted these because this guy is symmetry unique, so he'll be B1 by himself. This is in C2V. These two combine to make a B1 orbital en route 2, right, just for normalization. And likewise, the N guys in an even combination can make a B1 symmetry adapted basis function. And then the anti-symmetric combinations of these two guys and these two guys likewise make A2 orbitals. And now we've got a B1 problem and an A2 problem, and we know that we can treat them individually. Okay, so let's deal with the B1 problem first of all. We're going to need some matrix elements. So we need to give these some labels, huh? Let's call this phi1, phi2, and phi3. Okay, and I'll make up some approximations as we go. So first of all, I need to know what is that matrix element. Well, phi1 equals, and let's call the p orbitals p1, p2, p3. This equals p3, which is a Coulomb integral. We'll call that alpha. All right, how about phi2? Well, what this is p2 plus p4 and these are both en route 2. So I have en route 2, I have that twice. So I'm going to put a half there. And this equals a half. Now if I break this up, I'm going to break this up into, and now I'm going to use a shorthand notation. I hope you'll not get too upset. But we've got the H22, we've got H24 plus H42 plus H44. Now, these two guys I'm going to call 0 because these two orbitals are too far away to interact very much. So I'll call those 0, and then this guy and this guy are energies of unhybridized p orbitals. So that's the Coulomb integral. And so it's a half of alpha plus alpha equals alpha. Now, I'm going to assert that the mathematics for figuring out phi3 is just exactly the same as phi2, right? Except instead of where I have a 2, I'll have a 1, and where I have a 4, I'll have a 5. And then it just comes out to be the same. And so those basis functions all have got energies of alpha. So I'll start to fill up my matrix. H equals, okay, alpha, alpha, alpha. All right, what are the off-diagonal matrix elements? Let's figure this out. So let's do 1, 2. Phi1, H, phi2 equals P3, yeah? H, and then, well, let's do, what's it, 2 and 4 on root 2. P2 plus P4 on root 2, which equals 1 on root 2 outside of basically H32 plus H34. And because 3,2 and 3,4 are neighboring carbons, they have got a strong resonance integral, and we'll call those beta. And so this is then root 2, or it's 2 on root 2 times beta, so that's going to be root 2 beta. Okay. There. And the Hamiltonian matrix is symmetric, so I don't need to work out H21. What else do I need to work out? Well, maybe you'll believe me that H13 is going to be 0 because these orbitals are too far away. And so I'll put a 0 here, and I'll put a 0 here, and that leaves us to work out 2, 3. Okay. In terms of phi 2, 3. All right. My nomenclature needs, my notation needs some help. All right. So 2, 3 is P2 plus P4. Now both of these are going to be on root 2, so I put a half out like that. And P1 plus P5. Okay. So that's a half of 2, 1. I shouldn't write that. No, some symbol. I'll call this H21 plus H25 plus H41 plus H45. Now 2, 5, we'll call it 0, 4, 1, we'll call it 0, 4 and 5 are next to each other, 2 and 1 next to each other. All right. And so this is going to equal 1/2 of 2 beta, which is beta. All right, so then I've got a beta here. All right, so then we can solve that problem easily enough. Again, it's the determinant that needs to be solved will have a minus epsilon on the diagonal, and then here root 2 beta, and here root 2 beta, 0, and 0. And so there are only 2 terms in the diagonal that don't have a 0 in them, which is basically that diagonal, so alpha minus epsilon cubed. And then running that way runs into 0, that runs into 0. Running backwards there is then minus alpha minus epsilon times root 2 beta squared, probably. No?
2 beta.
No, it's just that guy. So that's just beta
Oh,
squared.
that one, sorry.
Right?
One more term?
I think so.
This guy.
Oh yeah, what did I just do? Oh yeah. So it's another
Oh
term.
yeah, so there's that one, and there's also that one. Yeah.
Alright. And so this one is 2 beta squared, right?
Yeah.
So does that make it a total of 3 beta squared?
Nice.
Does that make sense? I don't know what the viewers at home think. If we make the substitution, x cubed minus 3 beta squared x, this is now going to equal 0, we then solve and we get something like x equals 0, and then this would have like x outside of x squared minus 3 beta squared, and so it'd be like plus or minus, how do you do plus or minus? Plus minus root 3 beta. Does it make any sense? Does anyone care? Okay, so then those B1 orbitals are like then alpha plus root 3 beta, alpha minus root 3 beta, and alpha. So those are the B1 orbitals. B1, B1, and B1. Beautiful. Okay, how about the A2s? How are we going to do with A2? We can do it quicker. Well, there's only one off-diagonal matrix element to figure out. The diagonals are going to be alpha again. You can figure that out for yourself. And the off-diagonal matrix element is going to be basically, I'd say beta. It's my guess. But let's work it out. So let's say, I don't know, off-diagonal matrix element is going to be, so this is P2 minus P4, H, P1 minus P5, yep. all on 2 because we had a root 2 and a root 2, they multiply together to give a 2 on the bottom. Okay, so this comes out to be an H21 minus H25 minus H41, but then plus H45 all on 2. Those things are 0 because 2 and 5 and 4 and 1 are a long way away from each other. That's beta, and that's beta on 2 equals beta with beta with beta. So this is the standard 2 by 2 degenerate problem, which splits into alpha plus or minus beta, which will come in here. Alpha minus beta, alpha plus beta, and these are the A2 orbitals. And so 5 orbitals in a row split up into 5 orbitals, nicely, beautifully spaced. And that's that.